So what's that 12.011 over there for carbon? So here's a mass number, here's an atomic number, but that 24 here for the mass number for magnesium, that only applies to that particular atom of magnesium. Because we could have magnesium that has a mass number that is higher than 24 or lower than 24. We get that number because of these things, isotopes. You've all heard of this before, right? Isotopes. The reason that carbon has a 12.011 mass number over there on the periodic table is because that is the average weight. And so if we take all of the carbon atoms that exist in the atmosphere and then take a representative sample, so that let's say we take 100 of them, and then we weighed all of them, 89 of them would be carbon-12. 10 of them would be carbon-13. And 1 of them would be carbon-14. And if we averaged all that out, that's where we get the 12.011. Isotopes. So for example, magnesium here, there's an isotope. You notice the bottom of this? It's kind of hard to see. Kind of small. Magnesium has an atomic number of 12 for all of these, right? But the mass number is either 24, 25, or 26. What's different? It's all just magnesium, right? Same number of protons. What's different is the number of neutrons. Isotopes.
Is that like a rule of thumb? Like it goes up to?
No.
Okay.
It is not.
Okay.
Especially as you go up, for some of these deeper ones, it can go up by significantly more. It can jump up by 2, jump up by 4. You can jump a big gap.
Well, we don't need to know that for this.
Isotopes are simply different. They're the same atom, or by way of element, right? So same number of protons, different number of neutrons. So they're going to have the same properties as all the other atoms, with the exception of the stability of the nucleus. Certain nuclei aren't stable. It takes a certain arrangement of protons and neutrons to make a stable and therefore non-radioactive nucleus. Carbon-14 might be being made constantly by the sun in the upper atmosphere, but it's also constantly breaking down. Because a carbon nucleus with 14 protons is not stable. 12 and 13, those are perfectly stable. They'll last forever. But carbon-14 does not. It decays and becomes something else, not carbon anymore. Uranium, by way of example, something that all of you are probably familiar with as a radioactive thing, right? Uranium. It decays into lead. A specific isotope of lead. If we had done chapter 5, we'd know all this already.
Isn't carbon-14 have a shelf life of like 5,000?
5,072 years, or something like that, yeah. Which is why you can only go out about 10 half-lives. Beyond that, there is so little of it left that we cannot accurately judge if you've gone 10 half-lives, or 12 half-lives, or 25,000 half-lives. But we can tell if you've only gone 2 or 3 half-lives. The half-life of uranium is something like 800 million years or something. I'll look up half-life of uranium real quick. 100 million years maybe? Once again, this is chapter 5 stuff.
704 million.
704 million.
No,
7.04 million?
it depends on the isotope.
Uranium-235.
704 million.
Right. So that means that it takes 704 million years for half of the uranium that exists on Earth to decay into not uranium. But it doesn't just go it decays into atoms of something else. Which means we can measure how much of that new thing is there and how much of the uranium is there. And then we can do some math to find out how long it would take for that much of the new stuff to show up, and that tells us how old that thing is. We can use uranium dating to date dinosaurs, but not carbon dating, because dinosaurs are too old. It's also difficult to use uranium to date dinosaurs because life doesn't collect a lot of uranium in bones. So we usually have to use the date of, we have to date the rock that we find it in. Or rock layers that we find below and above it. But that's why it's laughable. You'll find evidence like, carbon dating this dinosaur, blah, 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 blah. Like, you can't, I don't care what your results were, you can't carbon date dinosaurs. There was one guy that argued about how the Earth is only 6,000 years old by carbon dating a dinosaur that he took a sample from a museum. So he illegally took a scraping from the bone, snuck into the museum and took a scraping from the bone and then sent it off to a lab to be carbon dating. There's so many problems with this, not the least of which being the bone that he took a scraping from had already been shellacked. So he was literally scraping off the clear paint and sending it to a lab to be carbon dated so that he could be like, you're all full of crap, dinosaurs are only 2,000 years old. Anyway, isotopes. An isotope is the same element, but has a different number of neutrons. And the only reason why that matters is because it changes the math. When you're doing math later on, it's what determines that number beneath, and in some cases, it's what makes them radioactive. So here we have that. We've already talked about that, right? The symbol, the atomic number, the mass number. You can answer all of this, right? What element it is, how many protons, how many neutrons, how many electrons it has. If I gave you all but one of these things, or if I gave you that, you can tell me everything, right? Okay. There we go. Now's when we bring it in. Atomic mass, 22.99 for sodium. It's because the calculated weight is based on an average of all naturally occurring isotopes. Based on the comparison to a mass of carbon-12. It's not the same as a mass number, because you will never find a sodium element with a mass of 22.99, right? Just like you're never going to find carbon with a mass of 12.011. It's either going to be carbon-12, carbon-13, or carbon-14. But when we do math later about making 1 mole of carbon dioxide from this reaction, you're going to assume that the weight of 1 mole of carbon dioxide is based off of that 12.011. Because unless we're really good about getting our carbon and making sure it's 100% carbon-12, the proportion of isotopes in our sample of carbon is going to be the same as the proportion of naturally occurring isotopes, and so that number is going to be accurate. But that's why all of those values have a lot of decimal places. Because almost, if not every element on the periodic table has more than one isotope. Even hydrogen. Carbon 12, 13, 14, oxygen 16, 17, 18, sulfur 32, 33, 34, and 36. That was the question earlier, right? Like, there's no 35 here. It's not naturally occurring. Potassium 39, 40, and 41. Copper 63 and 65. Uranium 235 and 238, I think, are the 2 primary isotopes, if I'm recalling correctly. Because uranium 235, I think, is the most common naturally occurring one. Uranium 238 is the one that you want to get a lot of if you want to make nuclear bombs. Try and make a nuclear bomb out of uranium 235 and you're not going to get anything. Because uranium 235 is too stable. Uranium 238, now that's the explosive bit. But in order to make an atomic bomb, you need a big chunk of almost entirely uranium 238. So in the news recently, the whole Iran deal thing, what were they doing? Why were we so concerned they were developing an atomic weapon? Because they were enriching their uranium. You may have heard stories about centrifuges. Why would Iran be using centrifuges to enrich uranium? Because that's how you get uranium-238. You spin it in really high-power centrifuges, and uranium-238, because it's got those extra neutrons in it, it's heavier, so what's it going to do in a big tube? It's going to shift to the bottom. So in order to make a big bomb, you've got to use a lot of uranium and spin it in big centrifuges for a really long time to get purer and purer and purer and purer, higher concentrations of uranium-238. Because if you use regular 235 in a bomb, it's just going to go... The 238 will go, but Some examples of isotopes of magnesium. What do you notice about the isotopes? What's the only number that's, well, the only number, what are the two numbers that are changing here? Mass number and number of neutrons. The number of electrons, the number of protons is not changing. Because if we change the number of protons, it'd be a different element. We can change the number of electrons, but that would make it an ion, and that's not what we're talking about. Where are we at? Yeah, we're getting there. So remember I told you about the different ratios of carbon? Here's the different ratios of magnesium. Magnesium has an atomic mass weight, right, of 24.31, the mass number. Atomic mass number 24.31. That's because 78% is magnesium-24. 10% is magnesium-25, and 11% is magnesium-26. So you do the averaged weight of all of those things, and you get 24.31. And so if you're going to look at an average sample of magnesium, if I were to measure the magnesium that was in any and all of your bodies, we would get roughly exactly that same proportion of magnesium, of those isotopes. Because life does not have a way of filtering out which isotopes it uses for magnesium. It's all just magnesium. So, without looking at these numbers, the atomic mass for chlorine is 35.45. If I told you that the two isotopes are chlorine 35 and chlorine 37, could you tell me which one was more common? Should be able to. I mean, I'm not going to ask you to calculate 75.76, but if the average weight is closer to 35 than it is to 37, then which one's more common? Have you heard that half of the people in America have a below average intelligence? You put up ching, because that's how we define average, right? So if it's closer to 35 than 37, then most of them are 35, right? Here's some tips on how to calculate. Get the abundance, multiply the percent abundance by the mass, and then sum it all up. This is just averaging, right? This is basic math. Okay, let's talk. 4.6, energy levels. We've got about 20 slides left, and over about an hour to go. So we're actually ahead of the curve even with my tangents, so let's take a 10-minute break. Get some drinks, go to the bathroom, stretch your legs, do something. We'll pick it up at 7:30, and we'll finish talking about what are the niftiest things about elements, and that's the way electrons work. Well, since I have time, I'll throw in some quantum chemistry, which I won't test you on, but you know, it might be neat to do during the video. Oh, that reminds me, I get it right here.
Okay, so it'll be like YouTube or something.
Yeah.
Thank you. I'm good.
Seriously,
I was really anxious about that, so here.
Essentially, the space ball will actually do instant video. Leave now, sir. Why don't we leave now? So. What's the matter, Colonel Sam?
We'll save this for halfway through the break.
Well, he said he'll give a link for it in the content.
For what?
With the videos of it, or
Yes.
class.
Right.
Yeah.
And this is one I rediscovered it today, so I might have to link up to this.
Okay.
I'll also play it. We're still here in 5 minutes.
My attendance is about to get real messy
Why is that?
for work.
Which reminds me. I think maybe it's the one I'm missing. Find out.
So the questions for the test, okay, so when I did the questions in the homework, they were significantly harder than what we practiced today. So would you say that for the test, they'll probably be more in line with what we're working on out of the book?
I would say that some of them will be about the same and some of them will be harder. And which ones you get will be completely random.
Are you making them up, or are you also pulling from the book for the
I
test
am.
as well?
I'm using the test bank that the publisher made,
Okay.
and then what I'm going through is, because I can't just import it all, which would be beautiful, but then also leans way too close to laziness, because then you just think, oh, I have to do that. For example, in the chapter 2 test bank, I found 2 errors. So the beautiful thing about this is what I have to do is I have to go in and manually convert their question into a form that I can import into D2L. And then for anything that involves math, and theoretically every other question as well, I have to read it. And then if I disagree with it, or if I want it, I rephrase it. And then I also have to check the math. So I'll double check the math and make sure that everything's okay. And then so one of the questions that I got rid of actually was because it was a question about the addition of significant figures in decimals. And the answer would have been correct if we were multiplying with significant figures, but was incorrect for the addition of significant figures. So I just got rid of that whole question instead of changing it up. And then there was another one that was talking about the number of significant figures in a certain equation, what you would end up with. And that was a true-false question, and so I corrected it and then kept it. So I double-checked them all, and then I put in there. And so a lot of the chapter 2 ones especially, I added using significant figures, because all of that math was under the assumption that it was significant figures, since that's a chapter-specific concept. So, but I tried to make sure that everywhere where it mattered, because there's sometimes where it didn't, is there's 5 options, but only one of them is anywhere near. So if you get 37.8 and the answer is 40, you know to pick that as opposed to 6 or 212, right? So I didn't care about those, but the ones where there's a 37.8 and a 40, like then it's like use sig figs. So yes, depending upon how the homework goes, that's an indication for me about how well everyone has absorbed how to calculate significant figures, right?
Yeah.
But that's half the point of chapter 2, so a lot of the questions are going to depend on that skill.
Yeah, I was definitely, I mean, I had like an email drafted to you at one point of like, hey, I think you forgot some specific pieces of this question.
And that is possible.
But it's not, I mean, but then I found the question in the book and it read exactly the same as the book and I was like,
Right.
oh god.
And that's what I mean by that's why I'm like, for the homework, I'm going to try as much as possible to use questions directly out of the book, but not the ones that are already graded for you. But right next to that question is another question conceptually very similar, and that does have an answer
That's what
for
they
you.
think. I was like, this is not anything close.
There is one homework question that I really liked, and I was like, ooh, I'm so happy to use it in the homework because it was just this neat little thing. And I think that's why it was worth 2 points, is because it required you to take this concept in math and do this concept in math, and then also realize that these 2 things are equivalent, and that's how you get your answer. Yes! I love questions like that. Because once again, that is that whole point of synthesis of like, I can say A, B, C, D, and I can say F, G, H, but if I don't know which one of these two things comes first, then I really don't know my alphabet. But if I can force myself to put them in the right order, now I can go from A all the way to H. So, yeah. That might be a question that you'll worry about.
Probably.
Most of the test questions don't get quite that complex.
Okay, good.
But as a homework question, I liked it because of how it took two mathematical concepts and required you to do both of those things in order to get the answer.
I think that's probably, this class is gonna make me an alcoholic.
Oh no, don't do that. Okay, most of you are back and it's not 7:30 yet, so we're gonna start this. I found that video. This goes beyond what we're doing in here, but it's cool. We're still technically on break. Here we go.
Thought isn't the best way to try to sum up how electrons come and go. They are the states of a matter field that follows an equation, the Dirac probe. The Schrodinger part of the whole equation will just lead itself, see when it expands. Now you like move them and let it in with the proton and watch them start to dance. Inside of it, it's like, oh proton, I feel your tug. Central potential, dip down, pulling on me. But I'm not pulling it deep. Know that would break uncertainty. Say, oh, electrons move too much. Slow down your pace and put that orbit on me. Come on now, follow my lead. Come on now, follow my lead. Orbitals take the shape they do. The stable states of the quantum rules. And when a one approaches,
We're not going to deal with orbitals.
this hydrogen has a room. It's found in nature as H2. Energy configuring a molecule. Diatomically bonding. Diatomically bonding. Diatomically bonding. Diatomically bonding. Energy configuring a molecule. When orbitals take the shape they do, that spin will give a lift on a twin. One up and down in the ground state. With this beam, quadruple degeneracy, the second shell can be filled up with eight. The higher angular power spread over beautiful flowers and minimal colors that come into play. Music drove the same see, but we're gonna make some money today. It's like, oh, atoms, I feel your tug. Now my electrons left are pulling on me. Come on now, settle around me. I'll hybridize to sp3, say, oh, carbon, here's our touch. We'll spread out 109.47 degrees. Come on now, follow our lead. Come on now, follow our lead. Molecules take the shape they do. Combining states of the quantum rules. I'm gonna show those sp2. Simplified on bonding. And as widely as ever view. It's spread in the molecule. The benzene and a ring they hold it true. Aromatically bonding. Aromatically bonding. Aromatically bonding. Aromatically bonding. The benzene and a ring they hold it true. When orbitals take the shape they do. Come bond with me, baby, come bond. 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 Polymers take the shape they do. Combining base like residues. Like urinase, ACGU. Look at hydrogen bonding. Peptides make a chain and group. And get a plate sheets and four screws. Secondary links they hold and move. They're all over your body. Come on with me, baby. Come on with me. They're all over your body. Come on with me, baby. Come on with me. They're all over your body. Come on with me, baby. Come on with me. They're all over your body. The chemical shape is best to do. The molecules take the shape of you.
Hey, musical side.
Science video of it!
Do you remember who it was that scraped the fossil? It wasn't Ken Ham, was it?
No, that was previous to him. He uses that though. Yeah. So does Banana Man.
Oh, can, break them free.
Yes. Yeah. Go both. I love that one. Bananas. Made to perfectly shape the hand, and blah blah, peeling with it up. That was like, you realize that we made that, right? Like we grew that, we bred that. When it was like, here, have a banana the way it was before we hybridized them and did all sorts of things to them to make them the way they are. It's like, that's not nearly as good of an example. But that's evolution. That's a whole different shelf that I probably shouldn't spend a lot of time harping on.
Give them some graces from New Zealand.
That's mean. There are plenty of people from New Zealand that are perfectly intelligent. All right. So we spent a lot of time saying the same things over and over and over again about atoms, right? Which is what chapter 4 is all about, the structure of an atom, properties of atoms. So that's why we said it over and over and over again. But electron energy levels, this is neat stuff. Why rainbows work the way they do, why they look the way they do, R.G. Biv, Roy G. Biv. Indigo is not a thing, but we don't spend a lot of time on that. So the way this works, the reason why we see rainbows the way that they do is entirely because of the electrical nature, the way in which atoms are built and put together. Quite literally, that rainbow is there because of the nature of the atoms around of the electrons in orbits around atoms of water. If we did not have water vapor in the air, if we didn't have rain coming through the air, we would not get rainbows the way we do. If it was instead raining drops of methane, we would get a different rainbow. Because methane has a different organization of elements, and therefore the way in which the electrons are going to bend and split light is going to be different. It's the reason why we discovered helium on the sun before we discovered helium on Earth. So, question?
Well, Herbert says that rainbows are visions, but only illusions, and rainbows have nothing to hide.
Except for the pot of gold at the end.
Do you ever wonder if colors are actually a different color, but our eyes aren't strong enough to see it?
Yes! But I don't wonder, I know it.
Oh, yeah?
Yeah.
What's the deal with indigo?
Indigo is not a color. So when we first defined Roy G. Biv, the guy who did that had this things for yes, but Roy G. Biv doesn't work if there's no indigo there. It's just Roy G. Biv. And so, but the reason why he threw indigo in was because Roy G. Biv is only 6 letters, and 6 isn't a spiffy enough number, but 7 is a special number. And not just because it's prime, but because it's special, like there's the angelic numbers, holy numbers, significant, like numbers that have spiritual significance, and 7's a nifty thing, and he was kind of had a, I was going to say something inappropriate. He had really liked some of these things, and so, so he threw indigo in there to make it 7 letters. Red, orange, yellow, green, blue, indigo, violet. There's no indigo. It goes from blue to violet. Like, what is indigo? It's purple. It's violet. So there's no...
So there's only 6 colors.
There's only 6 colors in the rainbow. Except for the fact that there's an infinite number of colors in the rainbow.
And then the 8th color, doctorine.
And then your brain goes... Because the ability to see colors is entirely dependent... Here's something to think about. Colors, and the only reason I'm spending any time on this is because I probably incorrectly think I have plenty of time to cover 18 slides. So, colors are entirely a construct of your mind. So the reason why you see this rainbow here is because there is light being, well, this is cheating because it's light being projected by a projector bouncing off of this, but the reason why you see it is because the light is bouncing off of this screen and entering your eye, and it is hitting receptors at the back of your eye which are responding to that photon of light by degrading a chemical. The act of that degradation changes the chemical nature of that cell, which causes an excitation of a of a neuronal cell, which then sends an electrical signal to the brain, and so the brain gets this. Hey. It gets a whole bunch of hey, because the brain doesn't see pictures. It gets information coming down neuronal lines, down nerve cells, and nerve cells have only one of two ways to be. They're either doing this, or they're doing this. Hey! And so, what the brain sees is, I'm getting a hey from these different neurons from the eye, and I know that that means that this cell was excited by light of a specific wavelength, and this cell is excited by light of a specific wavelength. And so it takes all that information and turns it into an image that you then perceive as the thing that you're looking at in front of you. Neat. So what color is a blue car? Every color except blue. Because the reason you see blue when you look at a car is because that's the color of light, the wavelength of light that's reflected off the car. So it's the color of light that hits your eye. All the other colors are absorbed by that blue paint and turned into heat. That's why black cars get hotter faster than white cars. Because black is the absence of color. Everything is absorbed and converted into heat. Whereas a white car reflects just about everything. And we see white light. But it's still just light hitting cells in the back of your eye, being converted into digital signals in your neurons, that being carried to your brain reconstructing the image, and then somewhere in your consciousness you go, this is what I'm seeing. Which is why if you do things like, anybody ever find your blind spot? Like do nothing like, cover one eye, whatever sort of thing. Get a sheet of paper about that big. Draw an X on it, and about 6 inches to the right, draw a little circle about the size of the eraser of a pencil. All right? And then if you close one eye and hold it so that the X is in front of the eye that's open, and the dot is kind of off, I think it's off to the outside, I think. And then you just kind of move that back and forth a little bit. What you'll find is that at a certain point, you focus, you stare at the X that you drew, right? But what you're doing is you're looking at that dot in your peripheral vision. And at a certain distance from your eye, depending upon the distance you put the dot from the X, that dot's going to disappear. But here's the thing. It doesn't just go away and there's like this emptiness. Your brain doesn't go, oh my God, there's nothing there! Your brain goes, well, there's paper all around it, so I'm just going to fill in that dead space with paper. You know that there's a dot there because you drew it. But here's the thing. Your retina is behind, so all the cells that are responding to light, your rods and your cones, they're responding to light. The nerves that they're exciting are actually on the inside of that, the light side of that. So when they send a signal to your brain, I'm not an art major. Give me a break. When they send a signal to your brain, they've got to get that signal from the nerve cells to the brain. And so there's this thing called the where all of those nerves, they actually go through, all that signal goes through the retina. So there's a spot in your retina where there are no cells that can detect light. You guys may already know this. And that is called your blind spot. Which is not that annoying part in your rearview mirrors and when you're driving. It's actually something to do with your eye, where there are no cells that can detect light. But here's the thing, it's okay, because you've got two eyes. And so the part where this eye isn't seeing things, this eye can fill in the blank. Except when you close one eye. And now that other eye is the only information source you have. And the brain isn't going to just leave it blank. It's not going to be like, there's no information. It's going to make up. Literally, it will lie to you about what you're seeing. Best guess. Yeah. What we see, totally made up. We might be in the Matrix right now.
You said it digitizes it?
Yeah.
You need to say that?
Yeah. Because nerve cells only have one of two states. Not active or I should say polarized, or not polarized. So they're either going, or they're going, hey! They're not going, blue light, or that's a cow. It's just, hey!
No
That's it.
amplitude?
What's that?
No amplitude?
Nope. It's either full strength, hey, or it's nothing. And the same with pain. The way something that hurts a little bit versus hurts a lot is the difference between one proprioreceptor, pain receptor, going, hey, or a lot of them going, hey. If you get a lot of messages, the brain goes, wow, that must really hurt. If you just get a few of them, it goes, that must be minorly annoying. It's all digital. But let's talk about chemistry. Sorry. Breaking up a bit. Electromagnetic radiation. The reason why that wasn't entirely off topic with respect to light and the way our eyes work is because radio waves, they're in here right now. We just can't see them. There's energy passing through us from space. It is traveling through this room, through your body, and then down through the ground, or vice versa. I'm not sure which way we're oriented right now, depending on where that radiation is coming from. And you just can't tell. You don't know that it's there. It's invisible to you because we don't have any senses that can detect it. Our eyes can only detect a tiny little portion of the electromagnetic spectrum. But what's the difference between light we can see and light we can't see? Nothing. Bees can see ultraviolet light. We cannot. We can still detect it, primarily by how red our skin gets when we've seen too much of it, i.e. a sunburn.
I work in HR. One time we had an employee who said she was allergic to the electromagnetic radiation
Oh, yeah.
where she was sitting.
Oh, yeah.
So we had to go through the interactive process through ADA to try and figure out if there were any reasonable accommodations.
Faraday cage.
This would have been really helpful like 2 years ago.
It was, we knew all this 2 years ago.
Well, right.
But here's the thing. It doesn't matter how cray-cray somebody might be with respect to certain things. You still have to, like, if you have to work with them, you have to work with them. So if somebody's like, I can't stand being within 12 feet of peanuts. Okay. I'll eat my peanut butter sandwiches at home.
We also had a lady who said that popcorn, she was allergic to that and the smell of it could kill her. So we had to ban,
That's entirely possible.
we had to ban popcorn from the whole building.
Yeah. No, we were at Walmart, and I had one of my best friend's kid with me, and this lady got up my grill about how irresponsible it was for me to let him eat a peanut butter and jelly sandwich in Walmart. Because there could be people with peanut allergies in Walmart and that might kill them. I'm like, okay, technically you are correct. Well, I didn't say this to her. Because this is like, you don't get in an argument about this with someone who's rude enough to actually confront you about this in the middle of Walmart. But this one was like, yes, and I could be killed in the next 5 seconds by an asteroid that hurtles through space, breaks through the roof of this building, and hits me in the head. It's possible.
Next time, just look at her with your hands and laugh maniacally.
No, that's not nice. I laugh maniacally after I get home. Anyway, electromagnetic radiation, radio waves that we listen to and everything else, this stuff is real. Whether or not someone's allergic to it,
It's either like allergic or they were too strong.
Yes, right. Like standing next to a really strong magnetic field can screw you up. There's some cool research that they've done with FMRs or otherwise, where you can get somebody, you sit them down in a chair, and then you'd be like, all right, recite the alphabet, and you go A, B, C, D, E, and they have this thing that looks like this like half a Magneto's helmet, and they just hold it up to the back of your head, and you go A, B, C, D, H, I, J, and then they pull it like gone. Like that electromagnetic radiation just totally with your brain. But the thing is, it's your brain, and so you don't perceive it. So it's not like when you're saying it, you're like, wow, that sounds really weird right now. Because your brain is not able to, so it just totally screws it up, and then pull it away, and So yes, I highly doubt that they were standing next to a 100 Tesla magnetic field.
No, we weren't gonna like office building, we just let her pick her own seat. Like
Right.
walk around and see what feels the
Right.
best.
And that's the thing, if it doesn't really cost you any extra money, it's just like, whatever it takes to just get along with people, right?
Usually it's the ballasts in the
What I
first
could
nights.
have
So
said
don't
was
worry,
that,
we had to buy the covers with
Yeah.
Oh my
lights.
God.
They look like puppy pads.
okay, that might be a bit much. But, I mean, maybe there is a medical condition out there that I'm unaware of. Because the thing about severe allergies to peanuts, you can have an allergy that is bad enough that you go into anaphylactic shock just from a tiny number of those antigens that are in the air because it can be aerosol. Sort of. The frequency of someone being that severely allergic is so incredibly rare. So maybe there is a thing that I'm just unaware of. My daughter's allergic to peanuts, enough that her class doesn't get to have peanut butter sandwiches. But her reaction is her lips get a little puffy. But we have EpiPens at home, so what I could have said was, it's okay, ma'am, I'm prepared. But, you know, like,
I'm just wondering if that enabled bees to pollinate ultraviolets.
well, it does. No, it doesn't allow them to pollinate ultraviolets, but what it does do is it means that when you look at a field of flowers, bees are seeing myriads of flowers with patterns on the petals because they can see ultraviolet. They can see ultraviolet light, and we cannot. So it looks like a field of just perfectly normal yellow flowers. For bees, there's myriad of patterns in all of these petals because they can see the ultraviolet light reflecting off of those petals that we cannot. So, X-rays, microwaves, the colors of a rainbow, the radio that you listen to your car, that is all exactly the same thing. It's just electromagnetic radiation. Light. It's just not necessarily visible light. The distance between the peaks of that wave, of that electromagnetic radiation, is what we call the wavelength. High energy radiation has shorter wavelengths. Low energy radiation has longer wavelengths. So here we have the visible spectrum right here, where we go from red, orange, yellow, green, blue, indigo in there somewhere, and violet. Right? That's visible light. There is still light above that and light below it. We call the light below it infrared. We call the light above it ultraviolet. Ultraviolet is the stuff that gives you sunburn. It's also the stuff that bleaches your pictures in colors if they're out in sunlight. Infrared is heat. Microwaves down here, radio waves down here. Really, really, really low energy emissions. By the way, anybody figure out how we discovered? Anybody know how we discovered infrared? When we started learning about the nature of the radiation that's here, somebody got this nifty idea that because prisms will break light up, right? If you take white light from the sun, but they did this experiment where they took white light from the sun, they put it through a prism, and they went, look, all of these nifty little colors. Well, then what they did was they took all those colors and redirected them back together through a prism in the opposite direction and got white light out on the other end. So we knew that white light was made up of all of the other colors of light because of that experiment. So someone got this nifty little idea, well, if these different colors of light are all in white light, there must be something different about them. Maybe what's different about them is their ability to affect temperature. And so they took a prism with white light, and then on the ground where the different colors of light were laid out, they laid down thermometers to determine if different colors of light had different temperatures. And then, but as a control, because you need controls, right? You take another thermometer and you put it outside of all of the light that you can see. And they happen to put it to the left of red. Off to the side where there was no visible light. And guess what happened to all of the thermometers in the visible light section? Bupkis. Guess what happened to the one that was over here to the left that wasn't in the visible light part of that prism? Temperature shot up. Because this is infrared. What are we seeing when we use infrared goggles? We're seeing heat signatures. Infrared light, red light that is below, lower energy than this light, is heat. We cook with infrared light. We cook with microwaves. Specifically because microwave radiation down in this area is just the right amount of radiation to excite the water in our food. Here's the thing. If you use sunlight and put it through a prism, this is what you get. All the colors of the rainbow. And if you were a bee, the rainbow would go past violet. But if we take something else, if we take a non-white light source, like burning, like the light that comes off of certain elements, like you can take a copper wire and you can burn it, and it will burn green. If you take that light and pass it through that exact same prism, it will separate out, but instead of giving you the whole spectrum, instead of giving you the rainbow, it will give you very specific lines of light. So it is the additive properties of all of these different colors of light that make that green light green. It's mostly green light, but there's some blue and some yellows and some reds and oranges in there too. Why? And if we picked a different element to burn, we get a different organization of lines. How did we discover helium before we found it on Earth? Because we did this with special filters from light from the sun. Because there's helium in the sun. And we could find these bands of light coming from specifically helium in the outer layer of the sun. Because we didn't know how to isolate it on Earth enough to get an isolated source to energize it enough to see what its pattern was. But why? Why do we get these different patterns? It's because of the energy levels of the electrons. I have an hour, right? Yeah.
You don't have to use all of it.
Okay, I'm told I'm supposed to use. I'm not supposed to let you go early. So far I haven't had that trouble.
That gives you an hour 4 minutes.
What's that?
Hour
Yeah, there you go. I'm okay with fudging a little bit, but you know, like, oh, we're done in 20 minutes. See you guys. Like, if that happened, we'd actually start on chapter 6. But really, that should have been my goal, because 6 is huge. But anyway, the reason that we get those emissions is because of the energy levels of electrons. Now, we're going to talk about assigning principal quantum numbers, if you will, which that might sound scary, principal quantum numbers, but you can just think of it as energy levels or atomic shell number levels, sort of. It's not exactly equivalent, but we're not going to get into orbitals because of this book, at least not until much later if we do it all. The lowest energy level is 1, the highest energy level is 7, so as the number goes up, the amount of energy level in electrons within that shell also goes up. You can think of it like bookshelves, where the lowest shelf at the bottom and higher shelves going up. The difference is, the higher you get, the amount of difference in energy levels between them gets smaller every time. So the biggest jump in energy level is going to be between 1 and 2. And then 2 and 3 is a little bit smaller, 3 and 4 is a little bit smaller, 4 and 5 even smaller, 5 and 6 even smaller. Here's the thing. You have a bookshelf with 7 shelves. I give you a book, and you put it on one of those shelves. How many different places can that book be? Could it be halfway between shelf number 4 and shelf number 5? Just kind of hovering in the air? Maybe if you have, telekinetic powers, sure. But if you follow the metaphor in normal application, no, it has only one of 7 places that it could be, right? On one of those 7 shelves. The same is true of electrons. Electrons in these different shells, in these different energy levels, these different quantum energy states. The reason why we call it quantum chemistry or quantum mechanics is because we can quantify how much energy is in a certain state. They only come in very specific states. So, that means that we can calculate the energy difference between the second shelf and the first shelf. We can calculate the energy difference between the third shelf and the second shelf. I'm not going to ask you to do those calculations, but it can be done. And therefore, if I were to move a book from one shelf to another, and this is where the metaphor breaks down because moving books doesn't release energy, but if you are an electron moving from one shelf to another, it would. It requires energy to move, and shifting back down to a lower one releases energy. And so the release of energy moving from 4 to 1 is going to have a very specific amount of energy that is released. And so the organization of electrons that you have in an atom, and how they can be excited and what they can do when they relax, means that they will release different levels of energy based on how they are organized as an atom. And that is what will determine each one of these wavelengths of light. Each one of these wavelengths of light is one specific measurement of how much energy is released when an electron relaxes from a high energy state to a low energy state. And different atoms have different nuclei, which means they organize their electrons in different ways, which means their shells will be organized differently, which means their pattern will be different, right? When you excite an electron by adding energy, when it relaxes, because it can't stay excited forever, when it relaxes, it will release most, if not all, of that energy. And it will release it as light. Here's the thing. In our chemical reactions that we've talked about, we say that we will never destroy or create matter, right? We will never destroy or create atoms. But we destroy and create photons constantly. Another little metaphor for you to appreciate. Tonight when you leave class, it'll be dark. If it's not cloudy, which it might be because we're expecting thunder, so tonight might not be the best night. But the next time you're outside and it's dark, look up. What will you see? Stars. Some planets too, but mostly stars. Why? Here's something to appreciate. The moment that you look up and perceive the twinkling of that star, what you have just done is marked the end of a millions of years journey for a photon that was released by a star millions of light years away, traveled through empty space for millions, if not hundreds of millions of years, before it finally entered Earth's atmosphere and hit the back of your eye where it was destroyed. And the energy of that destruction caused one specific nerve cell to react enough to let your brain know, light just hit me. You kill photons that have been alive for hundreds of millions of years every time you look up at the night sky. It's okay, you don't have to feel bad, because if your eyes weren't there, the photons would have been absorbed by the grass or this pavement or whatever was beneath you at the time. So you don't have to feel bad. Maybe that makes those photons special, because they hit your eyes instead of the pavement.
It seems like such a vicious cycle. Like
I
they're
know!
made up of a bunch of dead stars that kill photons and
It could either be a vicious cycle or it could be a beautiful cycle. It's your choice.
That could be of entropy.
a bunch of dead stars made up of really nothing.
Yeah, made up of mostly empty space.
Yeah.
We have such high opinions of ourselves though, don't we? Alright, so electrons that absorb energy, different amounts of energy will excite them and then lower them. Here's the thing though. These electrons on these shelves, they have to absorb exact amounts of energy too. Like you can't raise a book up to that midway point between the 5th and 7th shelf. If it won't raise it to exactly another shelf, it won't absorb it. But when it releases, if it does get raised up, when it releases, it will release a very specific amount of energy in response. And that is what gives us these different photons being emitted by these electrons that are excited and then relax. Here's the arrangement of photons. So, atomic number of 1, right? 2, 3, 4, 5, 6, so we're just going down the list. Hydrogen to helium, then back to lithium, beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine, right? So what's happening every time we go up? We're adding one more proton. With the addition of every proton, what are we also adding? One more electron. Well, the electrons are in the outer shell. So, our first atomic number is right here. Hydrogen has 1 atom. Helium has 2. But where is helium on our periodic table over here? What is helium? It's a member of a special group. We have a special name. What do we call it? Noble gases, right? Okay. So, helium is a noble gas. It only has 2 electrons, but that's because that very first shell, that very first shelf, it can only hold 2. So when we get to 2, it's done. It's full, right? That's why it's a noble gas. It doesn't want to react. Its outer shell is full. It's good. When we move up to lithium, lithium has 3, so it still has 2. What do you notice about this number of electrons in energy level 1? Once we get to 2, does it ever go higher? No, because that first shelf can only hold 2. Done. Lithium has 3 total, so the first 2 are going to go on the first shelf. Where do we got to put the one that we got left? Second shelf. What do you notice as we keep going down? 1, 2, 3, 4, 5, 6, 7, 8. And then once we get to 8, does it ever get higher? No. Nope. So if we get all the way down here to sodium, which has 11 protons, right? So we have 11 electrons. The first 2 go on the first shelf. The next 8 go on the second shelf, but that's only 10. We've got 1 left over, so we have 1 that goes on the third shelf. And then what happens as we keep going down the periodic table? 1, 2, 3, 4, 5, 6, 7, 8. And once we get to 8, we get potassium that has 19. So you have 8, 8, and 2, but that's only 18, and we've got 19 total. So where's that extra one got to go? Onto the 4th shelf. Where's potassium on our periodic table? In the metals, right? What's it got to do to get down to where its outer layer is completely full? It's got to get rid of one of these guys, right? It's got to get rid of that guy. And so now its outer layer, the top shelf, is full. To follow the metaphor here, what's happening is these atoms want their top shelf to be full. And they will do whatever they can to get that way. They will either gain or lose electrons so that their top shelf with books on it is full. So yes, we've got a 4th shelf here. But if we lose that 1 electron, that 1 book, then we've only got 3 shelves with books and all the shelves are full. That is where potassium likes to be.
But would it also try to go the other way?
It could. But it would take a lot more energy to force potassium to add 7 more electrons than it would take, or than you would get by just letting it let go of 1. Because either way, it would be in a stable state, yes. But a potassium at a charge of -7 is still a very highly energized atom. A potassium at a charge of +1 is much lower energy.
So when does it decide which way it's going to go? Like if it's halfway there, like what if there's 4 in the next? Oh, okay.
Right about there.
Okay.
That big dark line on the periodic table? Right about there. That's why we call these the metalloids. That's why they're semiconductors. Because if we tweak them the right way, we can make them good at conducting electricity or bad at conducting electricity, so they're sort of metallic, but also sort of not metallic. Whereas our guys out here, especially our halogens, they're going to be like, give me one more! Chlorine's not going to give up 7 electrons. It's going to get one more. The higher the bookshelf, the higher the energy level of the atoms, even if they're just sitting there. And this is why I want you to appreciate something. Hydrogen only has 1 electron, but it's got all of those shells. It has all 4 of those shells. In fact, it's got 6 shells, 7 shells, 8 shells. But it's only got 1 book. And if we give it enough energy, we could move that book to the 2nd shelf, or the 3rd shelf, or the 4th shelf, or the 8th shelf, and then when it relaxes, it's going to jump all the way down to a lower shelf, and every time it does that, it's going to give away however much energy it takes to move, right? And that would give us our spectra for hydrogen. But it's most stable if it has 1 electron in that lowest shelf. Potassium down here has a whole bunch of electrons, and most of its inner shells are already full. You can excite an electron from those lower shelves up to higher ones, and it can drop back down again, but the lowest it can get is still fairly energetic compared to hydrogen, because hydrogen only got 1 book, it's only on the bottom shelf. So more electrons means more potential, but I don't want you to think, taking the metaphor entirely too far, I don't want you to think that hydrogen only has 1 shelf. It has just as many shelves as everybody else. It just only has 1 book. So the options are a lot more limited. And it starts at a much lower energy state because that 1 book is going to be on the bottom shelf. Here we have a bunch of slides. They're going to pretty much say everything that I just told you. Right? Hydrogen has 1, helium has 2. So if we're going to arrange this though, what you can do, and there are, I should point out, the ability to do this might be important for homework or tests. Doing this, writing this electron arrangement, is something that you should be able to do. But, since it's an open book test, you could also just kind of cheat and look at this table. Because if you're going to write out the electron arrangement for oxygen, what would it be? 2, 6. It's 2 in the first shelf, 6 on the second. For chlorine, 2, 8, 7. But what does that mean? Yes, you can just look this up, but I need you to appreciate what that means. It means, especially this 7 at the end here, this is telling you how many valence electrons. This is telling you how many books are on that last shelf. Because that is the same for oxygen, sulfur, selenium. It's the same for carbon and silica. Why is it where they're like, well, what if it's non-carbon based life form? Why couldn't it be silica based life form? Why is that a question? Because silica has many of exactly the same properties as carbon. Why? Because it has the same number of electrons in its outer shell. It can make the same type of bonds as carbon, sort of. Because it also has 1 more shell. And so it's not quite as flexible because it's bigger. In the same way that I am not as flexible now as I was back when I was 40 pounds thinner and stretched more. I could assume a lot more positions than I can in my more rotund state. So silica has very similar properties to carbon, but it can't do everything carbon can do. Because it's got more books on more shelves. But it has the same number of books on that top shelf, right? The number of valence electrons is going to become very important for us later, because that is what determines the way in which we react to other chemicals. When we start making chemical combinations, when we start reacting carbon with oxygen to make CO2, things like that, it's these valence electrons that are the most important ones. So being able to understand how to do this, how to make this table, could you fill in this table? If I gave you a table of just elements and their symbols, Could you fill in this table? I hope that you could. Possibly. Maybe if you peeked at this one first and then looked at the blank one and did it, right? That first shelf can only hold 2. Done. Every shelf after that can hold 8. You should put a tiny asterisk next to that statement because we're going to figure out that some of them can actually hold 18. The fourth ones. The fourth ones and down can hold 18. Where do those extra 10 books go? All of these transitional elements right here in the middle. 2 on the first shelf. 8 on the next shelf, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 on the next shelf. 1, 2, 3, 4, 5, 6, 7, 8. 8 on the next shelf as well, unless we get full to 8, in which case then we start filling in down here. But we're not going to get that deep, because this is introductory chemistry, so. But doing this is important. It will be very important later. Once that first shelf fills up, you start counting up on the second. Once the second shelf fills up, you start counting up on the third. Theoretically, once the third shelf fills up, you start counting up on the fourth, right? We stop here at calcium because that's critically important, but we don't break into these transition elements there. Here's the thing. Higher energy levels, 5, 6, and 7, can theoretically accommodate 50, 72, 98 electrons, but they're usually not completely filled. The math gets weird when you start getting into these lower level elements. The number of potential spaces for books gets weird when you start getting into those lower elements because of specific energy states they can be forced into. But that's well beyond what we're going to talk about. A critically important understanding of the nature of chemistry, which we've spent a long time kind of tiptoeing into, is that this same pattern is repeated over and over again. The nature of something is directly related to how much and the organization of the things that make it up, right? An atom, the nature of an atom is based on how many protons, neutrons, and electrons it has, right? The nature of a compound is based on how many atoms, the number, organization, right? These are the things that give it its chemical properties. It's this same pattern that gets repeated over and over and over again. The reason that different atoms have different spectra, light emission spectra, is because of the organization of their electrons. How many they have and what energy states they start in determines where they can go and therefore what colors they will give off when they relax. That's why copper burns green. Chemistry leading to health. Seasonal affective disorder, on the subject of things that might not exist, but enough people experience it that we go like, oh, maybe it's a thing.
We've gotten word through that many times.
Right. And I could totally see somebody going, that's all in your head. Which is totally different, Rand, about how everything is in your head, because the only reason you can think you're here is because you have a brain that can appreciate its own existence, which makes literally everything inside your head. But let's not go there. So, seasonal affective disorder is a result of decreased serotonin, an increase in melatonin because you're not getting enough sun. Because in our modern day life, we don't spend, like, go back 2,000 years. I don't care if it's winter or not. It's cold and you're hungry. You probably got to go outside to get food, which means you're getting some sun. But how much sun do you get in the middle of January? I could time it. The amount of time it takes me to get from my front door to my car, from my car to the front door of LSC over at Mizzou, right? Like less than an hour, way less than an hour. During the summer, how much sunlight might I get? considerably more.
Well, it's not necessarily the amount of sunlight, it's the spectrum,
Yes.
seeing as the atmosphere blocks so much more of the spectrum.
Because of the angle of the inclination of light during the winter.
Right.
So how do we treat this particular thing? Well, we quite literally just give people lamps. My special lamps. It's not just, it's special lamps. My daughter was born with a high bilirubin count. So one of the nicknames that she got was glowworm, because for the first week that we had her home, for a few hours a day, we were supposed to like wrap her in this thing that was just this big honking, and it had this light pad thing. And so we wrapped the light pad so she was laying on the light pad so that she could get extra exposure to help the biological process to break down the remnants of inappropriate liver metabolism. Light is part of our biochemistry, not just because of the way our eyes work. Although I need to get more sun to get vitamin D, like most of that's a bunch of bull. Like we don't, it doesn't really work that way for most people. For some people they're particularly sensitive, yes, but go take a supplement. Because the damage that we take from being out in the sun. Anyway.
You'd be shocked how much light causes conflict at work.
No, I don't know that I would, but that's simply because I never underestimate the ability of people to find reasons to fight each other. Like it's in our nature. Because if you solve a problem, that like you'd think like, okay, now we can have peace, right? It's like, no, that just means that people have to find something else to fight about, which might be less serious of a fight, right? But you can have a knockdown, drag-out fight over a political, like for example, get into a political fight about whether or not we should have pulled out of the thing with Iran. Like literally, our opinions don't matter at all. But you can still have a fight with someone who's willing to like unfriend you on Facebook and never talk to you again because, like, why are we fighting about this?
I just never thought in my life I would be spending so much time with conflict resolution on whether the light should be on or not in a building.
See, I can appreciate the aggravation that might cause you, but I have an anecdote about that. Not that I care, but when I was working at the lab back at MS&T, it was a second floor building, a wall of windows, right? And so my computer was on the desk facing the windows, and so I would come into the room, sit at my desk, which was really just a space on the bench, and I wouldn't turn on the light because I've got the sun, yo. And the people would come in and be like, "Why is it dark in here?" Like, because I've got windows. Like if I was going to go to the other side of the bench and work on an experiment, I would turn the light on. But while I'm sitting at my desk typing, checking emails and stuff, like I don't need, there's plenty of light in here.
Some people just want to work in the dark.
Some people do.
It's awful.
Maybe they should work from home. Trends in periodic properties, 4.7. So here we have the electron arrangement of a bunch of atoms, right? We've seen this table before. Although now we're actually getting down to some of them where we're getting into these deep things. So here we have our 2881 for potassium, right? We're familiar with that. But you jump down here to gallium, which is 3A, right there. So you got gallium, 2818, 3. And that's because you're looking at gallium that has the ability to start throwing in things into these lower levels here, into these transitional elements. So it doesn't stop at 8 anymore, it's 18. But how many electrons are there because gallium is right here, right? Where is it? Right there. How many electrons are in the outer shell, the valence shell of that atom? Even though there's 18 of them at level 3, how many of them are in the highest one? 3 at level 4, right? Which is exactly the same as aluminum, which is one step up, right? It also only has 3 in the valence shell. which is also the same as boron, which also only has 3 in the valence shell. And so a lot of the physical properties of these atoms are going to be very similar because they're in the same group, right? That's why we build them that way. Not exactly the same, but similar. So, these periodic properties, we're going to talk about atomic size, ionization energy, metallic character. They're going to change by following certain trends, and we should be able to recognize those trends, or at least understand them, understand why. The first and most important aspect from these groups is going to be something we've already talked about a lot, valence electrons, right? Carbon, same number of valence electrons as silicon. Nitrogen, same number of valence electrons as phosphorus. And arsenic. Anybody remember hearing that big news report about the bacteria that could use arsenic instead of phosphorus? That they found in that lake? It was NASA that had a big press report about it. It was like maybe 5 years back, something like that. Why would that be a thing? It was a thing, potentially, because that's a big deal. Arsenic is toxic, right? Except that there are bacteria that can survive in a lake that is so heavy with arsenic that if you drank it, it would kill you. And here are these bacteria growing, happy as a lark. They're the only thing growing. But they figured out how to do it. And as much as that's neat that life can survive in environments that are inhospitable to life, the way we normally think about life, it would be even cooler if that life had actually learned how to use arsenic instead of phosphorus, because arsenic was much more common in that lake than phosphorus. Why is that even biologically feasible? That would be like me saying, hey, it'd be neat because some of my atoms, instead of using carbon, they're using chromium. No! But why is it feasible that arsenic could replace phosphorus? Because they're in the same group. They have the same number of valence electrons. Therefore, they would be able to make many of the same bonds. The problem with this was that when other groups went in and looked, they didn't find any evidence that arsenic was actually doing that. So, in other words, this was NASA jumping the gun and not going through a peer review. They got a little overexcited and just did a press release instead. Shouldn't have done that. But it's neat, because if it had been true, it would have expanded the potential of what life could look like. Places where you could incorporate other atoms that are not as common.
She's still sticking by her.
What's that?
She's still sticking by her research.
Yes, but other people have pretty much said, like, look, we can't repeat it. There's no evidence that there's any new genes that could do it. There's no explanation for it. So it's one of those like, we're not going to base a large amount of funding on your findings, right? Group number lines up with number of valence electrons, nice and convenient. That's why the periodic table is arranged the way that it is. All right, let's talk about a shorthand way to draw atoms so that you can have a better appreciation for how they're going to react with each other. And that's by using the Lewis dot structure. So, the Lewis dot structure is a shorthand way to appreciate the way in which atoms can react to each other to form polyatomic molecules. Because remember, it is the valence electrons that are going to be doing this reaction. It's the valence electrons that are going to be shared between atoms. Why? Because all the other atoms and all the other shells are already full, right? So why would that atom need to share those electrons? Now, in some cases, we can force it to. Special cases, we can force it to. Kind of like saying, can we add 7 to sodium instead of subtracting 1? Right? We can force it to happen. But for the most part, we're just dealing with the valence electrons. How many are in that outer shell? The top shelf. So if we take aluminum, aluminum has the electron arrangement of 2, 8, 3. So That 2 is the first shelf, can only hold 2, so it's full, we don't care. 8 is the second shelf, can only hold 8 in this case, so where it's full, we don't care. 3 left in that upper shelf, and so what we're going to do is we're going to arrange those 3 dots around the aluminum to show that it has 3 electrons in order to share. Now what is its desire? To either lose those electrons or to gain enough electrons to completely fill up its outer shell, right? Here's an example of magnesium. Magnesium is 282, so it's got 2 dots, 2 valence electrons, so we're going to put 2 dots. Now, here's the thing. We do not draw it like this. Why not? That's still 2 dots, right? What do we know about electrons? All of them have the same charge, right? So, why would they hang out right next to each other? If we're using this dot structure as a metaphor for how they're spread out, right? Why would they hang out right next to each other if they're both negatively charged? Would they do that? No. They would hang out anywhere else. Any of these are correct Lewis symbols for magnesium. But the 2 dots right next to each other, not correct. What's the only way that we could get 2 dots next to each other?
Covalent bond.
Yes. Covalent bond would be one way to do it, although we wouldn't draw it with 2 dots at that point.
Full
Oh,
shelf.
we could. Full shelf or a partially full shelf. So what would we have to have? If we put a dot, so the first one would go there, second one would go there, third one would go there, fourth one would go there. Where would we put the 5th one? Is there a 5th side? Nope. So now we'd have to put 2 of them together. Not because they want to be there, but that's because there's no other place to go. And we could put it there, or we could put it there, or we could put it there. Right? If we did this, by the way, just for purposes of mildly out-of-the-box discussions of methods, what would this be? What's the charge on that magnesium molecule, or magnesium atom? If it actually did have that Lewis dot structure, if we had managed to force it to be that way, what would it be? So what's magnesium with 0 charge? How many dots?
It'd be polar.
Yes, it would be polar. Well, no, it would be charged, but not polar, because it's one atom. It doesn't have a positive or negative side. It would be very negative. Because what did we have to do to get 5 dots around it? We had to add how many electrons? 3. So it would be magnesium minus 3. Because it's got overall charge. Overall it has 3 more electrons than protons, right? Because we had to add 3 electrons to get that many dots, right? So, we're going to get there, but that's not what Lewis is talking about quite yet. So, here's magnesium. So here's an example of the dot structure for the periodic table, at least with respect to the top 3 rows. So we kind of shoved it together for the top 3 rows, but here's dot structures. This is really convenient if you're on a homework or test question where it's asking about what's the correct dot structure, because you could just look this up, right? You know, if you want to take the time to find the spot in the book where it's at. And you've only got 2 hours, yo, so some of this you should just kind of know how to do somewhere, right? But theoretically, you can just look this up. Why is it that helium, neon, argon, and krypton?
Yeah, krypton.
Right?
Yeah.
Why is it that they don't react with anybody? They're full. They don't need to. Their outer shell is already full. They don't need to share with anyone else to fill up a shell. Alright, so that's the Lewis dot structure, to appreciate how many valence electrons there are. What about atomic size? The size of the atom is determined by the distance of the outer shell to the nucleus, right? You know those like Russian nesting dolls? You like pop it open, there's another doll on the inside, pop that open, another on the inside. The doll is only as big as the biggest one you have. Like theoretically you could have just one little doll, right? Or you could put that inside one more, and now it's a little bit bigger. You could put that inside one more, now it's a little bit bigger, right? You can keep going. The size of the atom is going to be determined by the number of shells that it has. So as you go down in the periodic table from carbon to silicon, or let's say from helium to neon to argon to krypton to xenon to... Where do you go? What's going to happen to the size of those atoms? Get bigger. Another shell outside of the other ones means they're just going to get bigger. So as you go down, the size is going to get bigger. What's this thing right here saying? Ionization energy decreases. What else happens as you go down? As we go from, let's say, fluorine to chlorine to bromide to iodine, the atom is getting bigger, yes? But what else is happening? They have the same number of, not the same number, we're increasing the number of protons, right? But we're also increasing the distance. So the strength of attraction between the nucleus and those outer electrons is going down, right? Because the distance between them is getting bigger. We're getting more positives here, but we're also getting a bigger distance between them. So the energy of ionization decreases. We haven't talked about energy of ionization, but what do you think that is? The energy to do what? What is an ion? What is an ion? An atom with a charge. So energy of ionization is the amount of energy it takes to either add or strip away an electron. The amount of energy of ionization decreases because the attraction between those outer shell electrons and the nucleus is lower because the nucleus is so much further away. So if the pull isn't as strong, it takes less energy to yank an electron away. Make sense? Here's the thing though. So as we go down from helium to lithium to sodium, potassium, the size of the atom is increasing, right? And the same is true over here. Hydrogen over there. Helium to neon to argon to krypton, the size of the atom is increasing, right? That's as we go down the group. But what's happening as we go across the period? We're not changing what the outer shell is anymore, right? This period right here, period 2, that's the same shelf. But what are we adding every time we go across it? We're adding more protons, right? And more electrons. But we're still staying on the same shelf. So we're making the positive and negative charge even stronger. What happens when positive and negative charges get stronger? They get closer together. So the size of the atom goes down from left to right in the same group because the attraction between the positive and negative charge is getting stronger. It gets bigger as we go down the group here, excuse me, period here, down group here, because we're adding more shells. But on every period, on every shelf, as we add more protons, the size of the atom is shrinking, right? Here we go, ionization energy. The amount of energy it takes to pull off an electron, and therefore ionize or create an ion out of an atom. So it's no longer balanced. We no longer have exactly the same amount of electrons as we do protons. It now has a charge, a net charge, therefore an ion. Why would that take energy? Conceptually speaking, everything takes energy. You ever hear there's no such thing as a free lunch? It's true, there's no such thing as a free lunch. Even when you get a free lunch, somebody's paying for it, right? The same is true in chemical reactions. There's no such thing as a free lunch. Even when there is, entropy is paying for it, but we're not going to take too much time to talk about that. So, Ionization energy is decreasing as we go down. Why? Because the outer electrons are further away from the nucleus. But it's increasing as we go across the period. Why? It's going down as we move down through the group, right? Why? Because it's getting further and further away. But why is it going up? Why is it getting harder to strip away an electron as we go across the period? For the same reason that the size is getting smaller, right? Why did it get smaller as we go across the period? More protons, more electrons means they are attracted to each other more, right? So to pull one off, we have to pay even more energy to strip it away because it really wants to stay. By way of example, since we have a test coming up, and there's only 4 slides left, how can I ask a question about this? I ask this now because, A, we've been doing this for 3 hours, and I can appreciate that it's hard to pay attention now. B, we're going to have a test coming up pretty quick here, right? And I have told you when we first started that I do not suggest that you just read your notes over and over again as a study methodology. Because if you can't connect the dots, it doesn't matter if you know where the dots are or not. If you can't connect them, you'll never see the big picture. So, how could you make this into a test question? If you were me, if you were teaching the class,